Good morning. I am Giulio Bionni, the teaching assistant for this session, and we are waiting for the chair to connect. So let's allow a few more minutes, let's say 2 or 3 minutes for the chair to connect. Otherwise, I will be in charge for chairing this session. Thank you. And I see that the speaker for the first paper is already connected, as well as the one for the second paper. So I guess we are ready to start. Can you confirm you're connected and everything works well on your side? Hongi Shi, can you confirm you're connected and would you try to share your screen, please? Okay, I can see. No problem.
Hello, can you hear me?
Yes, we can hear you clearly.
Okay, sorry, there's something wrong with my laptop, so I'll use my cell phone.
No problem. Just
and I'll use my laptop to share my presentation. I'm so sorry for the for this issue.
Absolutely no problem. That happens.
Okay.
Okay, so if you want, you may go ahead and try to share your screen.
Yeah. Okay. Can you see my screen?
Yes, perfectly. It's full screen. Okay. So I will just introduce your work. So welcome everybody to the session 4I of the general track. I will be chairing this session until the chair hopefully connects. And we will start with the first work, which is deep learning-based crack detection on complex decorative surfaces of cultural heritage artifacts. And the speaker is Ongi Shi. I hope I got your name correctly.
Yes.
Oh, that's great. And please go ahead. The floor is yours.
Okay. Good morning, everyone. This is Hongyi Shi from the University of Missouri, Columbia, and I'll start with my presentation. Okay. So in museum collection management, condition assessment is commonly conducted for long-term preservation purposes. The assessments document the artifact condition, including existing damages, deteriorations, or any visible changes over time. And among different types of damages, crack is one of the most common and important indicators of deteriorations of cultural heritage artifacts. However, condition assessment usually relies on visual inspection, which can be time consuming and may vary depending on the observer's experience and judgment. So for this matter, computer vision and deep learning offer a possible solution for automated and non-invasive crack detection, making the assessment process be more efficient. However, decorative patterns on the cultural heritage artifacts can look very similar to cracks and then interfere with the model detection. So this study identifies factors that affect deep learning crack detection performance under complex decorative patterns. So based on literature review, we identified several key factors that may affect crack detection performance in deep learning. These factors include visual interference, for example, complex backgrounds, lighting variation, and specular reflections. They all may introduce crack-like patterns and reduce detection accuracy. And then the contrast between cracks and the background patterns. Low contrast and complex surface textures can make crack be more difficult to be distinguished from the surrounding materials on the artifacts. And pre-processing strategies such as image enhancement and noise reduction can improve feature visibility, but different pre-processing strategies may have different results to the model performance. And input resolution, higher resolution can better preserve subtle crack features, while lower resolution may lose more details. And also transfer learning, it can improve model generalization, but domain differences may limit transfer learning effectiveness.
Hongye, I'm sorry. I don't know if it's just my problem, but we cannot hear you now. At least I cannot hear you.
Hello, can you hear me now?
Yes, we can hear you now. The screen
Okay,
sharing was perfectly fine. I think the problem was just with your microphone and camera. Perhaps some kind
okay,
of standby in your phone. Just
okay.
try
I'm
to
so
keep your phone
sorry.
active. No problem.
Okay, can you see
If you
my
want, we
slide
can
now?
start. Yeah, we can see it. You can start from the previous slide, I guess, because we
Uh,
couldn't already hear you.
okay, okay. Uh, so this study has several main steps: data collection, image processing, annotation, model training, and evaluation. We started with the data collection. We collaborated with the Anthropology Museum at the University of Missouri, Columbia. We selected 4 hand-painted terracotta leaves from their general collection. And the images were collected over 3 sessions with a turntable, so we can took pictures from different angles and various distance. And we took the pictures of the leads uh, for their both the front and the reverse sides. In total, 490 images were collected, and after removing the repeated and blurred images, 481 images were retained. And we tested several image processing strategies to evaluate their effects on crack detection performance. We first applied lighting normalization to reduce illumination variation across images. And then we applied background removal and reflection adjustments to reduce visual interference from the surrounding background and specular highlights. We also enhanced the image contrast to improve crack visibility and try to minimize texture amplification. All the annotation works are done on RoboFlow website, and it is an open public data set. It can be accessed by the link. And because some of the patterns, they look really similar to the cracks. So after consulting with the museum professionals, we defined the cracks as thin and elongated linear features with visible depth cues in this study. And for model training, we used YOLO version 8 nano model for its efficiency and suitability for the relatively small data sets in this study. And we designed a series of ablation experiments to evaluate how different image processing strategies and different training configurations affect crack detection performance. The baseline model used only 200 images with only lighting normalization applied. And then we removed background and adjusted the reflection, specular reflection, to evaluate whether reducing visual interference could improve detector performance under the same dataset size. Then we expanded the dataset from 200 images to 481 images to see if the dataset has can affect the performance. And then based on the expanded dataset and the background and reflection adjustment, 3 additional configurations were further tested. It includes contrast enhancement, higher input resolution from 640 pixels to 1024 pixels, and also transfer learning from a pre-trained infrastructure crack model. For the results, the quantitative results showed clear differences across the 6 ablation settings. The baseline model performed very poor, and after we applied background removal and reflection adjustment, it improved slightly. The largest improvement occurred after we expanded the dataset. It indicates that more in-domain training data is very critical for improving the model stability. Interestingly, contrast enhancement did not lead to a clear improvement. It is probably because when we enhanced the crack visibility, at the same time, we also enhanced We also amplified the crack like decorative patterns, surface textures, and even more noise. So it may increase visual interference and make the model more difficult to distinguish the crack and the background patterns. And similar to higher resolution input, the precision slightly, sorry, for the higher resolution input, the recall and mean average precision becomes higher, suggesting that it helps preserve fine crack details and allow the model to detect more true crack regions. But the precision slightly drop because the higher resolution images also make decorative textures and crack-like background patterns more clear, so it has more false positives in the texture areas. And for transfer learning, it has the highest and best overall performance, suggesting that it is more reliable for detecting the cracks and better overall detection quality. However, the recall is slightly lower than the higher resolution setting. So it probably because transfer learning is domain sensitive. The pre-trained model is learned from infrastructure crack data, which has a more simple background pattern in the um, more simple patterns in the background, while the target images contain decorative artifact surfaces. So as a result, the transferred features may support high confidence detections, but it cannot fully improve detection coverage. For the qualitative results, it further explains the quantitative findings. So in the baseline setting, we can see only very few cracks are detected, which is consistent with the low quantitative scores. And after remove the background and adjusted the reflection, the model detected slightly more crack regions, but the results were still fragmented. And with data expansion, the model showed a clear overall improvement. Um, more crack regions were detected as shown in the first images. The first image. However, in the second image, we can see the model still misses a lot of cracks. So it indicates that dataset expansion improved detection coverage, but did not fully resolve the difficulty of detecting crack on decorated surfaces. It shows a great improvement in contrast enhancement setting. It detected more cracks in individual examples, but the results became more fragmented and some regions appeared repeatedly detected. So it kind of explains why the quantitative improvement was limited. And the additional detection did not constantly improve correct crack coverage and may have introduced more false positives. For higher resolution, the qualitative improvement is not as visually obvious as the quantitative results. The detection still remains somewhat fragmented. However, compared with the contrast enhancement, the quantitative results show higher recall and mean average precision. So it seems that although higher resolution improved overall performance across the test set, visual complexity continue to affect the constancy of crack detection. And transfer learning, it got the best result. Most of the cracks are identified correctly, suggesting the model have a better detection reliability and fewer false positive. It is consistent with the high scores in quantitative results. We also do the external evaluation to further assess whether the model can be generalized beyond the internal data set. So we selected 3 unseen pottery artifacts. We used the overall best performance transfer learning model to test the external evaluation. The results show constantly high precision but pretty low recall. So it means that the model's detections are usually correct, but many actual cracks are missing. And the external evaluation also reveals some more limitations of the model. For example, the cup. The thinner cracks on the cup can be correctly identified, but the thicker crack cannot be recognized. It is because the internal dataset includes only the thinner cracks. And the fruit stand achieve the highest recall, likely because the geometric pattern is more regular. However, in contrast, the last artifact had the lowest recall because it has the most complicated patterns, create a strong visual interference. So overall, the results suggest that the model generalized conservatively. It can detect some cracks accurately, but it still struggles to cover all crack regions on the unseen complex decorative patterns. So we can get some insights from the internal and external evaluation. The above experiments shows that crack detection on decorative cultural heritage artifact surfaces is strongly influenced by visual interference. For example, the background, the reflection, and decorative patterns. And background removal and reflection adjustment can improve the result, but they are not sufficient to fully address complex decorative surfaces. Data expansion produced the most stable improvement, suggesting that representative in domain data is very critical. And visual enhancement introduced trade-off. For example, contrast enhancement and higher resolution, it enhanced the crack visibility, but at the same time, it amplified the background patterns, so create stronger visual interference to the model. And the transfer learning model show the best results, best performance in the internal evaluation. However, in the external evaluation, it cannot recognize different crack types, and it is still has a limitation on unseen or highly complex patterns on the artifact. So the generalization of the trained model depends on different surface conditions. So in conclusion, this study provides a systematic evaluation of how different preprocessing strategies and model configurations affect crack detection on decorative cultural heritage artifacts. The results shows that detection performance is condition dependent. Surface texture, visual interference, and pattern complexities strongly affect whether cracks can be accurately detected by the model. Dataset expansion, higher resolution, and transfer learning improve performance in different ways, but they also create trade-offs between precision recall and the detection coverage. So there is no one single best configuration for all cases. The future work, we are planning to expand more data, include more various different crack types, and include more different types of patterns to help improve the model generalization. And since we only used YOLO 8 for the model training, we are also planning to explore different models that are better suitable for fine elongated cracks. And that's it. Thank you. And sorry for the technical issues.
Oh, thank you. No, absolutely no problem for the technical issues. Thank you for the nice presentation. Is there any question? If not, I have a quick one. I've seen that the external evaluation
Yes.
tells mostly that the cracks detected are correct, but some cracks remain undetected.
Yes.
So did you try applying the same transformations you applied during the training process to the test set, just to have another look if any of the factors impacts more on the detection? So say, let's try to variate the contrast, for example, of the test images.
Sorry, can you repeat your question?
Yeah, so I mean, did you try to apply to the test set, to the external evaluation, or the transformations that you applied also to the training data to see if it has any impact and or if it allows you to detect more cracks, for example? Like trying to change the contrast of the test images, for example.
We only use the transfer learning model to for the external evaluation. We haven't tried the other trend model for the external evaluation. But it's a good insight. We can try to use other model. Maybe it can have a better result.
Okay. Okay, thank you.
Yeah,
So
thank
there
you
is a
for the
question from
suggestion.
there's a question from the room. So let's wait a second if they can use another microphone.
Hello?
And then proceed. Yes?
Can you hear us?
We can hear you.
Now,
Okay,
yes.
perfect. Yeah, perfect. So there's a question in the room.
I wanted
Yes.
to ask about the analysis of false positive, whether they analyzed the false positive of the metal. I mean cracks which are not cracks.
Were you able to hear? If not, I can
No,
repeat.
not very clear.
Is-
False positive.
Yeah, the question is regarding false positives. How was it then analyzed? If you have any cases where it detected some cracks that were not, in fact, cracks, just an overall view of the false positives.
I'm sorry, I don't get it.
How did you analyze the false positives in this data set?
You mean the wrong detection of the crack?
Yes, if there was any detection of a crack that wasn't actually a real crack.
Actually, when the model detects the cracks, the result is pretty accurate. The biggest problem of the model is it cannot detect some cracks, especially when the patterns is very complicated. But when the model detects the cracks, it is usually pretty accurate. But it has some repeated detection and fragmented detection.
Is that okay? Yeah. Okay, thank you.
Thank you.
Any more questions in the room? Nope. Yeah. No questions from here, Julio.
Okay, thank you. So we can proceed further. Just a reminder for the speakers, you have 20 minutes, including questions, so approximately 15 minutes time for your presentation. So let's move to the second work, which is classification of dynamic library signs related to the hospital context using recurrent neural networks. I think Pedro is online to present the work. Amazing.
Hello. Good morning.
So,
can you hear me?
Perfectly. So you can go ahead, Pedro. The floor is yours.
Okay. Can you see the screen well?
Yes.
Oh, well, okay. So I start. Hello, everyone. My name is Pedro Bittencourt from the Federal University of Juiz de Fora, Brazil. Today, I will present our work entitled Classification of Dynamic Libra Signs related to the hospital context using recurrent neural networks. This is a joint work with professors Luiz Maciel, Marcelo Vieira, and Saulo Vilela. Let me start with the motivation. Brazilian Sign Language, known as Libras, plays a fundamental role in the social inclusion of the deaf community. In Brazil, equal access to healthcare is guaranteed by law, specifically law number 13,146 of 2015. However, in practice, the situation in hospitals is quite different. Very few healthcare professionals are fluent in Libras, and this creates serious communication barriers that compromise the safety, autonomy, and dignity of deaf patients. In this context, our motivation is to develop a sign recognition system that can support communication in clinical environments, particularly during hospital triage. Well, to build such a system, we first needed a dataset of Libra signs covering this domain, and no public datasets of that kind exist today. To address this gap, we construct a dedicated dataset composed of 10 dynamic Libra signs related to hospital triage. The select signs represent common symptoms and medical conditions encountered in triage settings. They are allergy, autism, bronchitis, cramp, seizure, diarrhea, fracture, athlete's foot, heart attack, and measles. These are all dynamic signs involving coordinated movements of hands, arms, and body posture. 9 participants fluent in Libras performed each sign up to 5 times, resulting in a total of 492 videos. One participant was recorded twice under different conditions, varying clothing, accessories, and hairstyle. Recordings were made indoors with controlled lighting, a fixed camera, and a uniform background. For pre-processing, since the duration of each sign varies between participants, we resampled each video to exactly 30 frames. The frame selection follows a normal distribution centered at the central frame, which prioritizes the most relevant movements without discarding the rest. We also apply geometry data augmentation, mid rotations, translations, and spatial cropping to reduce overfitting. For feature extraction, we used MediaPipe Holistic, which gives us 33 pose landmarks and 42 hand landmarks, 21 per hand, that totaling 75 three-dimensional landmarks per frame. We discarded facial landmarks because facial expressions were not sufficiently visible in some videos. And each video is thus represented as a tensor of size 30 by 225. Our model architecture is a 4-layer recurrent network designed for sequential landmark data. First, the fat-led landmark vectors are fed into an input layer. Then, a masking layer ignores null values that may result from occasional extraction failures. The core of the architecture is an LSTM layer that captures the temporal dependence in gesture sequences. It uses the ReLU activation function, and we apply recurrent dropout as a regularization technique to reduce overfitting without compromising long-term dependencies. We also tested GRU and bidirectional LSTM variants, but this didn't show consistent improvements over the standard LSTM. Finally, a fully connected layer outputs the class probabilities. And for evaluation, we used a leave-one subject out cross-validation with k equals 10, and each fold was evaluated 20 times. We report accuracy, precision, recall, F1 and F2 scores. So let's look at the results for the 10 class classification problem. With the best configuration, this model achieved an average accuracy of 83.83% with a low standard deviation of 0.72, indicating consistent performance. If we look at the confusion matrix on the right, we can see that classes like autism, diarrhea, and measles achieved high performance. However, some classes performed poorly. In particular, cramp had recall below 60% and athlete's foot showed difficulties in both precision and recall. Looking more closely at the matrix, we can identify recurrent confusions between specific pairs of signs. And this is the key inside of our work. The model consistently confuses three pairs of signs: allergy with athlete's foot, bronchitis with heart attack, and cramp with fracture. These confusions are caused by intrinsic gestural similarities between the signs in each pair. They simply look very similar in terms of movement. To address this, we propose a hierarchical strategy. Instead of trying to solve the full 10 class problem directly, we first merge the confused pairs and train a general 7 class classifier. Then, for each merged pair, we train a dedicated expert model that focus exclusively on distinguish the two confused pairs. The first step is the 7 class classifier, where the confused pairs are measured in single classes. As you can see in the table, the performance is dramatically better. All classes achieved F1 scores above 91%, and the overall average is approximately 96%. The merged classes, such as bronchitis plus heart attack and cramp plus fracture, performed particularly well with metrics close to 100%. This confirms that the confusion was indeed happening within these pairs. The second step involves three binary expert classifiers. From bronchitis versus heart attack, the expert model achieved 93.42% accuracy with balanced precision and recall. For cramp versus fracture, accuracy was 90.87%, and notably, cramp recall increases from below 60% to approximately 86%. The most interesting case is allergy versus athlete's foot, where we achieved 97% accuracy. For this pair, we discovered that the main distinction lies at the very beginning of the gesture. So we propose an adaptive gesture onset detection method based on motion energy analysis of the hand centers combined with Savitz-Golay smoothing. This allows us to automatically detect when the actual gesture starts and sample the relevant 30 frames from that point. Now, when we integrate the 7 class model with the 3 expert models, we recover the full 10 classification. The integrated system achieved an average accuracy of 92.44% with a standard deviation of only 0.78. Looking at the improved confusion matrix, you can see a significant reduction in class confusions. The gains are concentrated exactly where we expected, in the previously confused pairs. Cramp recall increases from 56.87% to 82.71%. Athlete's foot recall increased from 55.9% to 88.60%. Meanwhile, classes that were already well defined, like autism, diarrhea, and measles, maintained their good performance. We also conducted an additional experiment to evaluate generalization. An external participant fluent in Libras, but not included in the original dataset, recorded 60 videos, 6 per sign under controlled conditions, using a different device and specifications. Despite this difference, the hierarchical strategy achieved an average accuracy of 98.70% with all metrics above 98%. This is very encouraging, however, I want to be transparent. This is only one participant, so the reduced variability simplifies the task. A broader evaluation with more participants is still necessary. So to conclude, in this work, we propose a dataset of 10 dynamic Libra signs for hospital triage. We developed an LSTM-based recognition pipeline using media-pipe holistic landmarks. We identified intrinsic gestural confusion between sign pairs and proposed a hierarchical strategy with expert models to address them. This increased performance from 83.83 to 92.484% on the main dataset and reached 98.70% for an external subject. For future work, we plan to expand the sign vocabulary and participant diversity, explore attention mechanisms and visual transformers, and work towards real-world deployments in hospital triage scenarios. Thank you very much for your attention.
Thank you, Pedro, for your presentation. Is there any question from the room or from the online guests?
Not from the participants on the room, but I do have one. If no one
Yes,
else,
please.
yeah. Okay, so Pedro, congratulations on your presentation. Thank you as well.
Thank you.
My question is regarding how troublesome was it to create the second layer of merged signals that you had to build the what you call the expert models, because once you start adding new signals to this data set, you might reach new scenarios of similarity, and this seems like it could be a throttling part for this data set to grow. So I just want to understand how troublesome was it to do this extra step for this particular 3 cases that you mentioned?
Yes, it was quite a lot of work, but I think the most the most laborious part was only to test a lot of hyperparameters of our network, because it's only this the let me think a lot. Well, yes, was only define the hyperparameters of the network. It's the most difficult part to address the problems of these 3 configured pairs, not only another problems. I think to expand the vocabulary signs, I think the most problem is to find people who really is fluent in Libras. So so it's the main problem that we achieved in this work is to find people who definitely knows Libras. I think to develop the expert models wasn't the problem. The real problem is to find people who really knows Libras and wants to participate in the develop of a new expanded data set.
Got it. Thank you.
Okay.
Okay, so thank you, Pedro. If there is no further question, we can proceed with the next speaker, who is in person in the room I guess.
Yes. We have Bianchi here who is going to present. I just give me a couple minutes because he's using a different laptop, so I just need to bring his presentation to this one.
Of course, no problem.
Just 1 second. Okay, so let me just share my screen. And can you give me confirmation that you're seeing this?
It's turning on now.
I think you're seeing the
we're just seeing a
presentation.
black screen for now.
Oh, okay. 1 second then. Sorry.
It was the browser, but the tab was black.
How about now?
Perfect.
Okay, awesome.
Okay,
And you can start.
I will just introduce the paper, which is titled A Comparative Study of Prompt Engineering Strategies for Data Visualization Scenarios. And Bianchi Serike McGinnis is going to present. Again, sorry for my surely bad pronunciation. And you can start.
Okay, you can hear me?
Yes, clearly.
Okay. Good morning. My name is Bianchi. Today we present our paper entitled Comparative Study of Prompt Engineering Strategies for Data Visualization Scenarios. This paper tried to investigate, it's an initial study, but tried to investigate how different prompt engineers' strategy can influence to create data visualization scenarios using large language models. Nowadays, generative AI is now able to support to create automatically data visualization scenarios. However, the quality of these scenarios depends strongly of the quality of the prompt. If the prompt is unclear or incomplete or presents ambiguity, the model may generate visualization. It's not expected for the user. Therefore, our main gap is understanding how different prompt engineers' strategy affect the construction of these prompts and the final visualization process. You have the main objective is to start to evaluate how four prompt engineers approach or strategy can influence the efficiency, the complexity, and the variability of the prompt construction. We organized the study around the four research questions. The first one investigates efficiency. The second one, we analyze the prompt structure and the completeness. The third one, we examine the variability and the consistency. And finally, you will study how visualization type and the analytical task, the visualization task, influencing user performance. Our contribution is focused on two main points. The first one is that comparative evaluation of the four prompt engineer strategies. And the second one to propose quantitative metrics to evaluate the prompt constructors. These metrics comes from the literature review and the other ones you proposed. In this study, you analyzed four strategies, as I said. The first one is no prompt engineer. In other words, users write prompted freely. The second one is a few short prompts. Users receive some visual examples of data visualization. It try to reproduce. The third is VQL. Is a structured prompt inspired in the query language. The first one is a hybrid approach, which combines the two last one. The experiment was conducted using ChatGPT 5.2. Participants worked with four prompt engineer strategies. You have four prompt engineer strategy, three types of visualization, bar chart, a line chart, scatter plot, and two tasks, identification and comparison. In total, we have a combination of 24 experimental conditions, and they use it to attempt to reproduce these images. For each experimental condition or scenario, the environment was configured with specific files and prompts. The basic configuration includes dataset, visual parameters, and initial prompt. For the few shots and the hybrid condition, you also include visual examples for each visualization technique. So the user has some example try to reproduce or inspired. This configuration helps guide the model and the standardized experiments. The quantitative analysis considers three main variables. Completion time is the time to complete the task. Measure how long the participant took to finish the task. Prompt length, measure the size of the prompt in tokens. Tokens is not necessarily a complete word, can be part of them. Prompt complexity, evaluate the structure of the instruction. You need to compose by the data visualization type, axis, and other encodes, for example. So we consider categories such as type, axis, as I said, aggregation, analytical task, information elements, and data format. The results show the prompt engineer did not make user faster. So you didn't see any statistical difference or big difference. VQL presents less dispersion. In the other words, the user more consistently do the tasks. Scatter plots were the most unstable visualization type. It's more difficult to finish. While line charts were the most consistent. This suggests the type of visualization also affects the prompt construction process. Regarding the prompt complexity, there was a little difference among the four conditions. In general, the participants produced prompts with similar levels of structure. However, scatter plot showed great variability. The type of the task, comparison, or identification had a little influence on the complexity of the prompts. The no prompt engineer condition had the highest standard deviation. In the other words, more variability. The highest, the means, it was the less stable condition, and VQL had the lowest variability, while the hybrid approach showed intermediate behavior. When you compare visualization techniques, bar charts require more time than line charts and scatter plots to build and try to complete the task. This may happen because the charts often require explicit categories, aggregation, and comparisons. In other words, you need more steps to conclude the task. The study also showed no significant difference between comparison and identification tasks. In general, the VQL and the hybrid approach reduce ambiguity. It's good for the quality of the prompt used. Based on the result, you can suggest different strategies for different users. Few short prompt, when you use the visual image as an example for the users, useful for beginners because the visual examples, and the task is more easy to conduct it. VQL is more appropriate for expert users who need precision or try to describe in more details the data visualization scenario. The hybrid approach is useful for users with different experience levels because it combines structure and examples. In this study, the hybrid strategy had the best overall performance. As limitations and future works, this study has some limitation. The participants were students. The experiment used only one larger language model, and three visualization types were considered. As a future work should include more participants, different LLMs, more visualization techniques, and the qualitative analysis of the prompts. This would help us better understand how users write instructions for visualization scenarios. So to conclude, this study shows the prompt engineering is important not only for improving performance, but also for making the user behavior more consistent, not in time, but in quality of the prompt. Structured strategy, especially VQL and hybrid approach, can reduce ambiguity and support better prompt construction. I'd like to thank you for the support from CAPS and my university UFPA. And then I open for questions. Thank you.
So, thank you for your presentation. Is there any question from the audience?
Yes. Can you hear us?
Yes, but if you could get closer to the microphone, maybe it would be better.
Eu não consigo ver aquela tela aqui.
Thanks for the presentation. It's not. Thanks for the presentation. So, do you hear me on the remote? Yeah. No. Yeah. Okay. So, to me, it's not clear what is the VQL.
VQL is like a language to consult the database, more structured. If you have a format, you can put the details. For example, what the kind of data visualization? You can put the scatter plot, bar chart, or line chart, for example. What attribute you can map for the X, a quality one, a categorical one, and so on.
this you have built this database?
No, but you can imagine the structure of the prompt. You have gaps. You need to fill the gaps with these instructions. The more structure. You don't have ambiguity. That's the idea. Because if you're free to type the prompt,
Yeah.
you can generate ambiguity or non-clear information.
So this VQL is a literature existing stuff, or you propose in the paper?
No, there is exists in the literature.
So okay, VQL is an existing stuff that we can
Yes.
we can use. Okay. Okay, that was all my. And so at the end, from the result, what in the time to build this graph, it seems that the manual stuff is more or less the same using.
Basically, you can see as a result those two main results: time and the quality of the prompt.
Yeah.
The time is not different in the four strategies, but the consistency and the quality of the prompt, you can see difference in between the approaches.
And
If you have no approach at all, you have the worst result as the quality of the prompt.
so when you give him the example, what do you give the Excel file or the image of the?
It's depending of the approach. For example, the few shots, I can give you the 3 to 5 images.
The image of the
Yes,
of the chart.
yeah, and try to reproduce together with describe. You need to do a chart like that, and you have some image as example.
And then I just finish. Okay, but I know that some stuff like Google Sheet, you can integrate Gemini with Google Sheet and ask to Gemini to create the chart directly from this sheet.
Yes.
I don't know if you where do you put this approach that I say in your scenario? What is the scenario that I say?
There are some description there, but in this example you gave me, you can obtain, can get not exactly what you want because you don't describe anything. You have the data, and the Gemini chooses for you the best visualization, but it's not the best for you, the best for him.
Okay. We could discuss.
Okay.
So, question is, actually, I don't understand your this proposed method. It's my question for experiment, for your experiment. So, page 10 is what is your baseline model for your experiment?
Page 10.
So,
This one here?
yes, your fuchsia, Wicker, hybrid, and what's your baseline SOTA model is you for comparison your proposed method.
So now here you compare it time. Okay, time.
Is,
Not the quality.
Okay.
Okay, just the time. This is an initial study. You to focus on just in quantity dimension. There's another paper for the future to try to the quality. I think this is our doubt. This is our doubt.
Yes.
Oh, okay.
So what is this IQR? I never heard this IQR is.
I didn't remember right now the name.
Interquartile range.
Yes.
Interquartile.
Yes. Thank you.
I heard about it, but I forgot the data from it. I had to catch it.
Okay, thank you. I do have one question. The times that you're showing here, they are the time that took the user to build the prompt, or the total time for the task to be completed?
The test to be completed. And the user needs to understand that he thinks the task is completed.
Yeah. Okay.
Got it. So, if there's any
Because remember, in some approaches, you have the examples,
Yes.
and you need to build your construction data visualization like that.
Uh-huh.
So, and I finished the job because I got the target.
But is there any case, or are you considering if you could take like multiple iterations with the prompt? For instance,
Yes.
I give it an initial prompt and then it gave me the wrong answer. So I had to retype or set to the chat.
They can retype many times.
And this is included in the total time?
Yes.
Okay, got it.
And many interactions.
Got it. Thank you. Julio, I think there are no more
Yes.
questions here.
Perfect. So we can proceed then with the fourth paper, which is entitled Detection of Cow Face and Subregions Using a New Annotated Data Set. Who is going to present the paper?
Hello, it's me again.
Oh, perfect. So welcome again, Pedro. And so you already know how to share the screen and everything seems to be working. So please go ahead.
So many links.
Okay, can you hear me? It's okay?
Yes.
Oh, good. Hello, everyone, again. I will present another work entitled Detection of Cow Face and Subregions using a new annotated dataset. And this work is a collaboration involving researchers from UFGF and Embrapa Dairy Cattle. So livestock farming is a key component of the global agricultural economy, with the cattle herd reaching approximately 1.5 billion worldwide. In recent years, there has been a growing demand for what we call precision livestock farming. Within this context, cattle facial subregions, ears, eyes, and muzzle carry valuable signals about emotional state, pain, and body temperature. Our motivation in this work is to develop an object detection method capable of identifying cattle faces and their key facial subregions in real-world, non-standardized farming environments. To the best of our knowledge, there is no public dataset or method specifically designed to detect ears, eyes, and muzzle in cattle, and that is the gap our work addresses. To address this gap, we created the Annotated Cattle Images Dataset, or ACI. It contains 7,146 images with over 54,000 labeled instances across 6 classes: cow face, left ear, left eye, right eye, and muzzle. The training set, which represents about 86.5% of the data, was built from images curated from open access platforms like Pixels, Pixabay, Openverse, and Unsplash using multilingual search queries in Portuguese, Spanish, and English. The test set, about 13.5%, was collected directly in real farms in collaboration with Embrapa Dairy Cattle. It includes 165 individuals of the Girolando and Holstein breeds. All annotation were done manually using label IMG. And importantly, this dataset is publicly available for future research. Our annotation process follows 7 key principles to ensure precision and consistency. The key ones listed in these slides are type bounding boxes, labels from the animal's perspective, and a deliberate looseness around eyes to avoid confusion with background. We also applied an image adaptation strategy. Images exceeding 15 megapixels were resized while preserving their aspect ratio applied only to the training set. Looking at the class distribution, we observed that larger facial regions dominate the dataset, while smaller regions are consistently underrepresented. This is caused by occlusion and the inherent difficulty of annotation in small regions. This class imbalance is important because, as we will see in the experiments, it directly penalizes the detection performance for the I classes. The figure shows the first stage of our proposed detection method. Our method has 3 stages, and the first one is preprocessing. Here, we split the original ACI dataset into 2 complementary sub-datasets. The first one, called ACFI, keeps only face annotations on full images. The second one, called ACFSI, keeps only subregions annotation on face cropped images. So from a single dataset, we derive 2 specialized views that will feed 2 independent models. The second stage is training. With the 2 sub-datasets prepared, we train 2 independent models, one for the face detection using the ACFI sub-dataset, and one for subregion detection using the ACFSI sub-dataset. Each model is specialized in its own test, which is the foundation of our 2-stage strategy. Finally, the third stage is prediction. At inference time, the face detection model first locates all faces in the input image. It detects face is then cropped to a 1:1 aspect ratio, resized to 640 by 640 pixels, and passed to the subregion detection model, which detects the ears, eyes, and the muzzle inside the crop. This process repeats for every face detected in the image. Let me explain the rationale behind this 2-stage approach. The key insight is that small targets like eyes suffer significantly when detected in full images. The background introduces too much noise and the objects are just too small relative to the image. By first detecting the face and then cropping it, we effectively remove the background and make the subregions much more prominent. Here we see the results for the first 2 problems. For all 6 classes in entire image, YOLO V9, sorry. I passed 2 slides. So we've evaluated 3 YOLO architectures, always using the largest variant available: YOLO V8X, YOLO V9E, and YOLO V10. Training details are in the slide. Horizontal flip was disabled because it inverts the face, and we evaluated 4 distinct problems: all 6 classes in entire images, face only in entire images, subregions in entire images, and subregions in cropped face images. And this last one being our proposed approach. Here we see the results for the first two problems. For all 6 classes in entire images, YOLO V9 achieved the best results. For face-on detection, YOLO V9 again leads, and notice all metrics are significantly higher. This makes sense because the face is a larger, more easily identifiable object compared to the individual subregions. This confirms that face detection is a relatively straightforward problem, which supports our decision to use it as the first stage of our pipeline. Now, this is the most important comparison. The top table shows subregions detection in entire image, and the bottom table shows our proposed approach. That is subregion detection in crop face images. Looking at the YOLO V9, which is the best model in both cases, recall increased from 0.728 to 0.826. MAP 50 goes from 0.764 to 0.864, and crucially, MAP 5095, which is the most challenging metric, improves from 0.388 to 0.472. That's a ugly 22% improvement on the hardest metric. And this clearly demonstrates that cropping the face before detecting subregions is an effective strategy. These confusion matrices make the improvement very visual. On the left, subregion detection in entire image. The right, in cropped face images. Notice how the diagonal becomes significantly darker in the right matrix. This means more correct predictions. The improvement is especially visible for ears and eyes, which were the weakest class before. The background confusion row also decreases substantially, confirming that removing the background through the face cropping is indeed the key design choice. We also built a complete application on top of our two-stage pipeline with two operating modes. The most prominent face mode detects only the largest face per image, while all faces mode detects every face. An interesting challenge we encounter is that when animals are close together, the cropped face region may inadvertently include a subregion belonging to a neighboring animal, resulting in duplicate detections. To address this, we implemented two post-processing strategies. Max confidence simply keeps the highest confidence prediction, and the advanced filter is more sophisticated, using geometry constraints between subregion and face, plus IOU-based pruning. Here are the application results measured by accuracy at IOU above 0.5. The advanced filter consistently outperforms max confidence, although the difference is modest. In the most prominent face mode, the overall accuracy reaches 85.77% with the advanced filter. Muzzle is the best performing class at over 94%, while eyes remaining the hardest classes at around 71 to 77%. The all-face mode shows lower accuracy, which is expected because smaller and less prominent faces are harder to process accurately. To conclude, we introduced the ACI dataset with 7,146 images with over 54,000 annotated instances, which is publicly available for future research. We propose a two-stage detection pipeline where the face is detected first, cropped, and then subregions are detected within the crop. YOLO V9 consistently delivered the best results across all experiments. The key finding is that face cropping removes background noise and significantly improves the detection of small subregions. Our application reaches 85.77% accuracy in the most prominent face mode. For future work, we plan to explore tiny object detection models to further improve eye detection and to investigate ensemble approaches for higher robustness. Thank you very much for your attention again, and I'm happy to take another any questions.
Thank you, Pedro, for the presentation. Is there any question from the audience?
No questions from here. Sorry. There is a question.
Okay.
Actually, I understand this proposed method is very reasonable.
I can hear well.
Just 1 second.
Okay,
Yeah, please try to speak closer to the microphone.
Well, I understand your proposed method, but it's all the performance evaluation metric are related to accuracy. So why wasn't the need to support real-time processing on edge device taken into account? Why their performance metric is also all related to accuracy?
To accuracy. And they didn't
Yeah.
account for the time?
Time.
Yeah.
Okay. You say about the inference time, yes?
Inference time?
Or
also, overall
processing?
Also,
one of them is.
Yeah.
Oh, okay. No, I think I understand. The time between the difference time between the modes are irrelevant, so we didn't use it as a metric. Is that the question?
Yeah, it's okay.
Yeah, and another question is why didn't you use the recent YOLO model?
Okay.
I know it's YOLO 11, 12, maybe. Yeah.
Okay. So we had trained with these models too. After the publication of the paper, but we haven't yet improvements in these recent models. The best results is the YOLO V9E model. Even we train with these recent models. The YOLO V9 maintains the best performance.
Okay, thank you.
Okay.
Thank you. I think there are no more questions from here.
Perfect. So in that case, we can move to the last presentation of this session, which is entitled Enhanced Architecture for Non-Destructive Leaf Area Estimation based on a Semantic Segmentation Network. And I think the speaker is Caio Duarte.
Hello, I will share my screen.
Yes, we can hear you.
Can you see my screen?
Yes, we can see it.
Yes.
Okay, so I'll start. Hello everyone, my name is Caio Seixas Duarte and I'm a graduate student at the Federal University of Juiz de Fora. Today I will present the paper entitled Enhanced Architecture for Non-Destructive Leaf Area Estimation based on a Semantic Segmentation Network, developed in collaboration with Professors Luiz Maurílio da Silva Maciel, Saulo Moraes Vilela, and Marcelo Bernardo Vieira. So leaf area is an important indicator of plant growth and physiological status. Traditionally, it's measured using contact-based methods, which can be time-consuming and even destructive. Therefore, image-based methods have gained increasing attention, especially with the advances in computer vision and convolutional neural networks. However, challenges still remain regarding feature representation and preservation of leaf details. So to reduce these limitations, we developed the approach presented in this work. So the objective of this work was to improve the non-destructive estimation of pin leaf area by enhancing an architecture based on an adapted deep lab v3 plus neural network. The proposed architecture is directly based on the adapted deep lab v3 plus model, which was used as the reference architecture. The main differences lies in the decoder responsible for leaf area estimation, where we inserted new blocks to improve the processing of the features extracted by the network. The figure shows an overview of the complete architecture. The encoder and the segmentation decoder remain unchanged. In the area decoder highlighted in green, we inserted the three new components, a one-by-one convolution, the CBAN model, and the C3K2 block. The main contributions of this work are concentrating in the area estimation decoder. After the feature concatenation stage, we first added a one-by-one convolution to improve feature fusion after concatenation. Next, we inserted the CBAN model. This block applies attention mechanisms in two stages, first over the channels and then over the spatial dimensions of the image. In this way, the network automatically emphasizes the regions and features that are most relevant for leaf area estimation. Afterward, we inserted the C3K2 block, which is responsible for refining the extracted features and enabling the representation of finer leaf details. Both CBAN and C3K2 have configurable parameters. Therefore, we conducted an ablation study by evaluating different configurations of these blocks to identify which provided the best performance. So to evaluate the proposed architecture, we performed a direct comparison with the reference architecture based on DeepLab v3 Plus using exactly the same experimental protocol. We kept almost all the training hyperparameters unchanged and only varied the learning rate and batch size. This ensured that any performance difference resulted only from the proposed architecture modifications. The models were trained for 150,000 steps. Then on the training set, we evaluated the checkpoints generated and saved every 100 steps between 145,000 and 150,000 steps, and automatically selected the best model based on the sum of the mean and the standard deviation of the relative error for both leaf and marker, considering the lowest value of this sum. Finally, the selected model was evaluated on the test set using the semi-relative error rate metric. The dataset usually contains images of common bean leaves still in the vegetative stage. Each image also includes a 5 by 5 centimeters fiducial marker used as the reference for the error calculation. In total, the public dataset contains 6,981 images with a resolution of 512 by 512 pixels, corresponding to 612 distinct leaves. Part of the experiments were evaluated using five-fold cross-validation, ensuring that the same leaf never appeared simultaneously in both training and test sets. For the ablation studies, we used only fold one, while the final evaluation considered all five folds. In addition, the reference architecture was also reevaluated and used exactly the same protocol, allowing a fair comparison between the methods. So after defining the proposed architecture, we conducted an ablation study to analyze the contribution of each inserted component separately. Our experiments used the same baseline architecture and were conducted on the first fold of the cross-validation. First, we evaluated different values of CBAN reduction rate parameter using the value values 2, 8, and 16. This parameter reduces the number of channels entering the CBAN channel attention models. Next, we investigate the impact of the number of bottlenecks in the C3K2 block by comparing architectures with 1, 2, and 6 bottlenecks. The bottlenecks are internal C3K2 models composed of convolutions and residual connections responsible for refining the features and extraction from the image. And finally, we analyze the different internal organizations of CBAN, special and channel attention models, comparing the original sequential configuration with channel attention followed by special attention, and the reverse order and the parallel configuration. We can observe that all the proposed configurations outperform the reference model during training. Among them, the architecture with a reduction rate of H achieved the best balance between the mean and standard deviation of the error for both the leaf and marker on the test set. Although the reduction rate of 2 achieved the lowest mean error during training for the leaf, it did not provide the best performance during testing. Therefore, we adopted the reduction ratio of 8 for the following experiments. In this case, architectures containing 1, 2, and 6 bottlenecks were compared while keeping the rest of the architecture unchanged. We observed that the configuration with only one bottleneck achieved the best results for leaf error estimation during both training and testing, while also providing competitive performance for the marker. Increasing the depth of the block did not produce consistent improvements, and in some cases even increased the estimation error. So these results indicate that a simple architecture was sufficient to refine the extracted features. Finally, 3 configurations were compared. First, channel attention followed by special attention, a sequential arrangement. Second, the reverse order, and finally, a parallel configuration. The original CBAN configuration, composed of channel attention model followed by special attention model, achieved the lowest errors for leaf error estimation. The other configurations obtained similar results in some scenarios, but non-consistently outperformed the arrangement originally proposed by the CBAN authors. Therefore, this configuration was maintained in the final experiment. After defining the best configuration through the ablation study, we performed the complete evaluation using all 5 folds of the cross-validation. At this stage, we calculated the relative error individually for each image in the dataset, and then computed the overall mean, avoiding bias associated with using only a single fold. And as shown in the table, the proposed model reduced both the mean and the standard deviation of the error for the leaf and the marker compared with the reference model. These results demonstrate that the proposed modifications provide consistent improvements and good generalization across the entire dataset. And now we analyze the prediction behavior at the image level, considering all 5 folds of the cross-validation. For this proposed, we use 2 types of analysis. The first consists of scatter plots relating the estimated leaf areas to the reference values. The second uses histograms to analyze the distribution of prediction errors. Overall, we observed good agreement between the estimated and reference values, with fold 1 achieving the best coefficient of determination. In addition, the markers show the lower error dispersion than the leaves, and most folds exhibit a slight tendency to underestimate the leaf area. This figure represents the scatter plot for folds 1, 2, and 3. In each plot, each point represents one image from the test set. The horizontal axis shows the reference leaf area, while the vertical axis shows the area estimated by the model. The fitted regression line and its corresponding coefficient of determination are also presented. We can observe that all folds show a consistent linear relationship between the estimate and the reference values. Fold 1 achieved the best performance, followed by folds 3 and 2. It's also possible to note some vertical group of points indicating that the same leaf may present small estimation variations under different image acquisition image acquisitions conditions. And this slide presents the results obtained for folds 4 and 5. As observed previously, the predictions continue to closely follow the reference values, showing that the model maintains consistent behavior throughout the cross-validation. Although fold 5 presents slightly lower performance than the others, there is still a well-defined linear relationship between the estimate and the reference leaf areas. And this slide presents the prediction histograms considering all 5 folds of the cross-validation together. On the left, we have the leaf area estimation errors, and on the right, the fiducial marker errors. Overall, most errors are concentrated around 0, indicate that the model produces consistent estimates for a large portion of the dataset. For the leaf, there is a slight predominance of negative errors, confirming the small underestimation tendency observed in the most folds. In contrast, the marker shows a much narrower distribution centered around 0, indicating lower error dispersion, greater estimation stability. And this behavior is consistent across all 5 folds and can be explained by the marker's more regular and well-defined geometry, which facilitates the segmentation and the error estimation process. In addition to the quantitative evaluation, we also performed a qualitative analysis of the model outputs. Each example presents from left to right the input of image, the segmentation result, the estimated error map, and the corresponding ground truth. In the first example, we observe a good result. Both the leaf and marker were segmented with high accuracy, showing well-defined boundaries and very homogeneous error distribution. Visually, the estimated error map is very similar to the ground truth, demonstrates the model's ability to correctly represent the objects in the image and correctly estimate their areas. And this second example represents a more challenging scenario. In this case, there is a greater perspective distortion and non-uniform illumination, making the segmentation and error estimation tests more difficult. As a result, we observe slightly larger differences between the estimated error mapping and the ground truth, especially in the marker region, where the error distribution became less homogeneous. Even though it's important to highlight that the model correctly preserves the overall object shapes and maintains good spatial correspondence, demonstrates robustness even under more challenging conditions. Based on the experiments, several observations can be highlighted. First, the marker showed a greater improvement than the leaf compared with the reference model. This can be explained by its more uniform and well-defined geometry, which facilitates the network's learning process. We also found that the C3K2 block achieved a better performance using one bottleneck, indicating that increasing its depth did not provide benefits for this application. Regarding CBAN, the results were obtained with a reduction rate of 80, suggests that the smaller reduction rates may provide better performance by preserving a greater amount of relevant information. In addition, changes to the internal arrangements of the model did not produce significant improvements compared with the original configuration. And finally, the results obtained across all 5-fold demonstrate that the proposed architecture has good generalization capability and consistently improves upon the reference model. And as conclusion, this work incorporated the CBAN and C3K2 models into a DeepLab v3+ based architecture for non-destructive leaf error estimation. The results show the reduction in the estimation error compared with the reference model for both the leaf and fiducial marker. This find demonstrate the potential for lightweight attention and refinement mechanisms for computer vision application in agriculture. And as future work, we intend to investigate new hyperparameter variations and evaluate the model on different datasets to further improve its generalization capability. And thank you very much for your attention.
Thank you, Caio, for your presentation. Is there any question?
We have questions in the room.
Please go ahead.
Okay, thank you for your presentation. So actually, I don't understand is your idea is DIMLab version 3 plus decode with integrating CBAM and C3K2 blocks. So is my question is what was the specific process for integrating CBAM and C3K2 block into the DIMLab version 3 plus decode? So how is it possible? Is
Can you repeat, please?
Yeah.
Can you repeat the question, please?
For your is a proposed method is my question is so how you to integrate the DIMLab version 3 plus decode read integrating CBAM plus C3K2 blocks. So
The question is, how did he integrate?
Integrate. How to integrate?
Yeah. So basically, how did you integrate CBAM and C3K2 with your overall architecture? How was this integration done?
Well, in this case, in the how can I say, the architecture of reference, we have an area decoder, and the main objective of this work is to improve the error estimation. So I wanna input this kind of blocks in the error decoder to turn the results better to error estimation, right?
I think you can see the difference in results from using the default decoder versus the area decoder with this integration. I don't know if that helps.
My adaptations is highlighted in green. The reference architecture don't have this green blocks.
Their evaluation studies. So your model is integrating CBAM and C3K2 blocks, but their able studies is not considered CBAM and C3K2 blocks. So why
why did he choose this?
Yeah.
Meaning between that and other alternatives?
Yes.
Yeah. Okay. So between CBAM and C3K2 blocks and their alternatives, why did you choose them?
Why? I'd like one attention model to I choose the attention model to improve the error estimation and to the error decoder focus on the more important parts of the feature map, the error decoder, and the C3K2 is to the network focus on the refine the features in the error decoder.
Did you look at some alternatives to them?
No.
Okay.
No. Actually, I tried to implement the self-attention model, but this has a high cost, computation cost, so I could not run well. So I had to change the attention model. So I chose the CBAM, as the CBAM don't spend a high competition cost, right? Low cost competition model.
Yeah. Okay. Thank you.
Thank you.
Okay, is there any other question?
Not from the room.
Okay, also online. So I would like to thank Kaya for his presentation again, and all the speakers
you.
that participated and all the attendees of this session. We can now officially close this session. And again, thank you everybody for your attention, and see you in the next sessions of the conference.
Thank you. Thank you, Julio.
Thank you.
Thank
Bye.
you. Goodbye.
Julio, is it okay if I just leave the call? I'm not the official chair, so I'm a little lost in here. Not sure if you're still around. Oh, okay.